everyone, I am Miss Hu, your physics teacher. In this video, we'll be going through measurement techniques, which is an introductory topic in the IGCSE Physics subject. In this video, we will learn to describe the use of rulers and measuring cylinders to find a length or a volume. Describe how to measure a variety of time intervals using clocks and digital timers, as well as determine an average value for a small distance and for a short interval of time by measuring multiples, which includes the period of oscillation of a pendulum. Now, for some of you, you might say, hey, I already know all this stuff, but I'm creating this video anyway, so that at least we would have covered everything that we need to know for our exams. We're going to start off first with the concept of measuring length. So when it comes to measuring length, you do of course need to know what the units are for length. The SI unit is meters, but you can also of course use other units which are acceptable in daily life. For example, you could use centimeters or millimeters. Generally, when it comes to measuring length, we would be using a ruler, or you could use a measuring tape like this or this, depending on what you're measuring. You'll be using this kind of measuring tape to measure straight distances. For example, if you're measuring the length of your table. However, if you're measuring the length of something that's circular, for example, the circumference of your waist, then this measuring tape would be far more suitable because it is flexible. When it comes to measuring volume, the SI unit is meter cube, but sometimes we do express a volume in milliliters. Now, if you can recall your math, the volume of a regular shape can be calculated using the volume formula. In this case, this is not quite measuring because you are calculating, but nevertheless, you should know that this is possible. And when it comes to physics, we do use a lot of basic math concepts. So whatever you've learned in math, we can definitely apply them in physics. So for example, if you wanted to obtain the volume of a cuboid, you could calculate it by using the formula for the volume calculation of a cuboid, which is length times width times height. When it comes to a sphere, we have to use the volume formula to calculate a sphere. So the volume of the sphere is calculated as 4 over 3 pi r cubed, where r is the radius of a sphere. Now in reality, we normally are not able to measure the radius of a sphere. Rather, we would measure the diameter. So if d was a diameter and r was the radius, we already know that diameter is double that of radius, or d equals 2r for short. So if you want to replace r with d in this case, that means we would write r equals d over 2. So the substitution in this case is 4 over 3 pi d over 2 cube. This would give us 4 over 3 pi d cube over 8. Now we're going to simplify this, so this gives us pi d cube over 6. So this is how you could calculate the volume of a sphere if we could measure out the diameter of that sphere. So it's a little bit complicated, but yes, it's possible. Just use math. When it comes to a cylinder, we need to get the area of the cross-section, which in this case is the area of the circle, times the length of the cylinder, or height if you look at it that way. So I'm just going to put some labels here so that we can see the symbols. In this case, I'm going to put this as L, and let's say this is D. So to get the volume of the cylinder, we start off first with the area of the cross-section, which is the shape of a circle. Area of a circle is pi r squared. So the volume of the cylinder is pi r squared times L. As with the sphere, we normally don't measure the radius of the circle, rather we're going to have to measure the diameter. So substituting the same relationship of d and r in this case, that means r is d over 2. We're going to square this times L. Simplifying this, we would get pi d squared L over 4. And that's how we're able to calculate the volume of objects which have regular shapes like these. If you have any other shape, you have to use the volume for those kind of shapes. For example, if you have a pyramid, then you need to use the volume formula for that pyramid. However, when it comes to the practical aspects of physics, we may not necessarily want to always have to calculate the volume out, but rather we want to measure the volume. So whether you have a regular or irregular shape, you can measure the volume by using the water displacement method. This is based on a discovery by Archimedes, who discovered that an object will always displace the volume of water that's equal to its own volume. So two ways of doing the water displacement method. One is by filling up the measuring cylinder with a certain amount of water, not to the top of course. You must give it some space for the water to move up. You'll find that every time you put an object inside, it will cause the water level to rise. That's because the object has displaced water. To displace here means to push the water away to make space for itself. So the volume of water that has risen here is actually equal to the volume of the object. So if we want to obtain the volume of the object, we just need to take the difference between the volumes of these two diagrams. That means we take the volume of water with the object minus the volume of the water without the object. Another way is by using a displacement can, also known as a eureka can. The term eureka comes from Archimedes' discovery of shouting eureka, eureka. So I'm not here to tell the story. Go and watch a YouTube video that talks about Archimedes and eureka. For now, let's just get into how we can use the eureka can or displacement can. A displacement can or a eureka can is a water container with a spout. We fill up the water up to the level of the spout. Ideally, you should fill up the water until the water overflows, and then the water will stop naturally, meaning that the water level is now just below that spout. So if you were to add on any water or place an object in the water will immediately spill over. So once it has stabilized to that level without any object in it, that means the water level is really just below that spout. Now we put the object inside, the object of which we want to measure the volume. The moment you place the object inside, the water is going to overflow. So obviously, you need to place a measuring device to capture that water, normally a measuring cylinder. So the water that has spilled out, we capture it in the measuring cylinder, and the volume of water that is captured by the measuring cylinder, that volume is equal to the volume of the object. So both of these methods are exactly the same. Both are using the water displacement method. The only difference is that this one, we just need to take the difference between the two volumes. And for this one, we actually force the water to flow out and we measure the volume of that water that has spilled out. So that's how we can measure volume. When it comes to measuring time, you can either use a timer or a stopwatch. The unit of time can include seconds, minutes, even hours, days, years. The SI unit of time, as you should know, is seconds. And normally in the lab, we use seconds because we are measuring quite a short period of time. You do have to be familiar with learning how to read analog stopwatches and digital stopwatches. If you'd like to explore more on this, do let me know in the comments below and I'll be happy to create videos on how to read the timers. Otherwise, I'm going to assume all of you know how to read these kind of stopwatches. Generally, for analog stopwatches, you can see that the larger face here is showing the time in seconds and the smaller face is showing the time in minutes. So every time you read an analog stopwatch, don't forget to look at the inner face. That's something that a lot of students tend to miss out. So this is seconds, this is minutes. A digital stopwatch is much easier to read. Normally, the number on the left here is minutes, this is seconds, this is the decimal point of seconds. So yes, a digital stopwatch is much more sensitive compared to an analog stopwatch. Now, let's look at the concept of determining small values using averages. What is this topic about? So, the thing is, when we want to measure very small values here mean values that are extremely small. For example, if we want to get the diameter of a wire or even the diameter of your hair, something that tiny. Do we have measuring instruments that can measure such tiny values? Yes, we do. We do have devices known as vernier calipers and micrometer screw gauges that can measure such tiny diameters. Or if you want to measure other small values, for example, if you want to measure a very short period of time, we can also get very sensitive timers to measure those. However, in IGCSE Physics, we want you to learn how to measure small values given the normal sized instruments. That means we're not giving you the small sensitive equipment. So we'll get some measuring instruments which are not sensitive enough to measure small values. Is it still possible to get the small value? Yes, we can. what we'll do is we'll use a concept of averages. So the average in this case, if we're taking it from math, we're using the mean values, where we get the total number of many divided by the number that we've taken. So if we can measure a large number of identical items and calculate the average, we will be able to get the small value for that particular measurement. Let's look at some examples. As I mentioned earlier, measuring the diameter of a wire. Now we know the wire diameter is extremely small, and if we try to use a ruler to measure the diameter of one tiny wire, you can see that the ruler is not able to show us that value because it's too small. If you get a single wire and you try to get the diameter, the ruler is just not sensitive enough to give us that exact value. So how do we overcome this? Take many of the same and get the average. So one suitable method is to take that wire, loop it around a pencil like this, and make sure that the wires are touching side by side. So the diagram here, I know is not showing it ideally correct because you've got space in between. This is not correct. You need to place them side by side with no gaps. They cannot even overlap, because if they overlap, you're not going to get the correct value, right? So you've got to place the wires side by side. So now, logically, you should be able to see that if you have many loops here, now we're able to measure the length because the value of length is now quite substantial. So by taking the length between the start and the end of the loop, take this length and divide it by the number of loops, you're able to calculate the average diameter of a single wire. Generally, the more loops you have, the more accurate the number would be. Besides that, you could also use this method to measure the diameter of a marble. So sometimes you may get an object that is, it's large enough to be measured with a ruler, but it may not still be exact because the diameter may fall somewhere between the two lines on the scale. So you'll be like, is it a 0.5 in this case, or a 0.4, could be a 0.7, you're not sure. So to overcome this uncertainty, you can do the same thing. Take many of the same kind of marbles, measure the diameter across many marbles. The length of all these marbles divided by the number of marbles will give you the average diameter of one marble, and that would give you a more accurate value compared to measuring just the diameter of a single marble. You could also use this method to measure the period of oscillation, and this is an experiment which you should have done in school. So if you did not get the opportunity to do this in school, or if you're learning physics on your own at home, you could actually do this experiment at home. Do check out my video on how to conduct the pendulum experiment in your own home. So the period of oscillation here means the time for one complete oscillation for the pendulum to move from one point to the end and coming back. Now, if the length of the pendulum is very short, the period of oscillation is also very short. You might find that if you're trying to take the time for just one period of oscillation, sometimes it's too fast for you to be able to react quickly. It's like by the time you release and press a timer, it gets back to its original position, completing one period of oscillation so quickly, you barely have time to press a timer again. So you got to remember that if it's a very short period of time, you won't be able to react quick enough. Again, how do we overcome this uncertainty? We take the time for many oscillations. So maybe 10 oscillations, 20 complete oscillations. So we take the time for those many oscillations and get the average. Total time divided by the number of oscillations to get the period of one oscillation. So this will enable us to be able to measure very short periods of time. Also, if you have very small objects and you want to measure the volume. For example, let's say we have small marbles. And if you want to get the volume of a single marble, we might not be able to get the exact value because although the marble can cause some water displacement, but the change in level here, the change in volume here may not be significant enough for us to be able to observe accurately. So, as we have been learning so far, the more objects we measure, the more accurate the calculation would be. So instead of measuring the volume of a single marble, what we do is we place a few marbles so that you can get a more significant change in volume. Then we can use that change in volume to get the average of a single marble, and we'll be able to obtain a far more accurate value. Now let's look at the concept of errors. Okay, first of all, what is an error? Now, before we go into the concept of errors, I just want to point out one thing. I always mention this to my physics students. In physics, you're going to come across some terms that are taken from the English language, where they're spelled like the original word, you pronounce them like the original word, and even when used in context, it seems similar to the original word taken from English. However, some of these terms are extremely specific to physics, meaning that they have a different meaning that we use only in physics. This is called jargon, and it's true for many industries, not only for physics. You'll see them used in medical industries, business industries, scientific industries, all kinds of fields. There's certain jargon, technical jargon or otherwise, where words are taken from the English language, you spell them and you say them similar to the English language, yet they have very specific meanings within that industry. So in English, you've learned the term error means mistake. In physics, it is something like mistake, but not quite. The term error specifically is used for measurements, and what error means is that it's a measure of the estimated difference between the observed or calculated value of a quantity and its true value. Wow, what does that mean? When it comes to measurements, when we measure something, obviously there is a particular value that is true. For example, if you were to measure the length of a pencil, the actual value could be something like 5.11 centimeters. Now, when we use a ruler to measure it, we're not always going to get the exact accurate value. Maybe you'll get a value like 5.1 or 5.2, or maybe there's a problem with the ruler and you get something like 4.8 centimeters. So the term error here means the difference between the actual value and what we've measured. To understand where these errors come from, we have to know about the different types of errors. Generally, errors can be classified into two categories: systematic error and random error. A systematic error means that an error that happens every single time we take a measurement. That's why it's systematic. Without fail, it's systematically always going to appear. Systematic errors are normally caused by the measuring instruments. So these errors could include zero error and calibration error. I'll explain this shortly in the upcoming slides. Random errors are errors which don't always happen. That means sometimes it could happen, sometimes it doesn't happen. So every measurement you take, you might or might not get that error. So these errors could be due to human beings, for example, parallax errors, human reaction times, and human mistakes, or could be something that's not a human error, but caused by something that's beyond our control. For example, changes in the environment. Let's just go through these errors in a little bit more detail. Let's start first with zero error. So an example of a zero error would be the edge of a ruler. For example, if we have a ruler where the edge starts exactly at zero, when it's brand new, not an issue at all, it's sharp, it's correct, it's exact. But as we start to use the ruler more and more, after a few years, you're going to find that it no longer starts from zero. That's because the worn out edge causes some material to be removed as time goes by. So if you assume the n was zero and you continue to use this at zero, the readings you're getting are now longer and longer. Why? Because the edge no longer starts from zero. It might have been shaved down to maybe 2 millimeters. So every reading you take now is added on with an additional 2 millimeters. So a zero error essentially means the measuring instrument does not start from zero. So besides a ruler, you could also have things like a weighing scale. I'm sure some of you have experienced this before, right? You step on a weighing scale, like, oh my God, how did I suddenly gain, like 3 kg overnight? And then when you step off, you're like, no wonder. The scale didn't start from zero. It started from 3. So every time you step on it, it's going to add on an additional 3 kilograms. So this is the concept of zero error. So zero error is when the measuring instrument does not start from zero. It doesn't always have to mean that the readings become higher. If, let's say, the scale started below zero, then the readings will be lower than the actual value. So just to point out to you before we move on, again, remember that the physics terms here do not have the same meaning as in English, because I've got students who say, oh, zero means none. Error means mistake. Oh, zero error means no mistake. That's not what it means. It doesn't mean, oh, there's no mistakes in the measurement. Okay, that's not what it means. Because like, oh, zero error in the reading. Oh, zero error, no mistake. So zero error here means that the measuring instrument has a non-zero start. So it didn't start from 0, and that's the problem. That's why it causes the reading to be inaccurate. Moving on to calibration error. So the calibration error here refers to an incorrect calibration. So you see, if the scale of the measuring instrument is not accurate, obviously the values taken will also not be correct. So for example, if you have a measuring device where the number it's pointing to is no longer correct. For example, if you have an ammeter, when it's supposed to be 1 ampere, maybe it's pointing to 1.2. And then when it's supposed to be 2, it's pointing to 2.4. So which means that the scale is no longer pointing to the correct value. So this is called an incorrect calibration. So to calibrate means to match the scale of the measuring instrument to the actual value. Now, what could cause calibration error? It could be a manufacturer fault where when a manufacturer produced it, the scale was wrong to begin with. I'm sure some of you have experienced this before, where the weighing scale, the number is completely wrong in the first place. Or you get a ruler where when you place it with your friend's ruler, the scale isn't even lining up to begin with. So every reading you take, obviously, the value is not correct. So it's not your fault, right? You know how to take the reading, but the scale is wrong. Or sometimes it could be a lack of maintenance. That means when the instrument was brand new, probably everything was correct, but as time passed, there is some physical fault that has caused the scale to be off, depending on the instrument. So for example, if you have a measuring scale which uses a spring, and the spring has gotten worn out with time, then what happens is the scale is correct, but because the spring is not responding the way it used to, then the pointer is no longer able to point correctly on the scale. So a lack of maintenance here means that we didn't upgrade or didn't change the parts that need to be changed. So calibration error is an inherent problem within the measuring instrument, and that's why every single time we take a measurement with that particular device, you're going to get an inaccurate value. Now, let's take a look at some of the random errors. Starting off first with parallax error. So the parallax error is one of the most common errors that can happen in reality, and that's why when it comes to your exams, the parallax error is always an error that must be addressed. If you don't place your eye at the correct position relative to scale, the reading will definitely be inaccurate. So what is the correct position? Now, to avoid parallax error, the eye must be placed perpendicular to the scale. So if we have an example in this diagram here, this is a ruler. The purple color thing is the object to be measured. The correct position is this in the middle, where the eye is perpendicular to the scale. The eye line is perpendicular to the scale. If you place your eye at angles like this, then you're going to get different values. So let's say in this diagram, the correct value as observed from the correct position, let's say 12 mm in this case. Now, if you place your eye at this angle, you can see how from the position of the eye at the tip of the purple object, we're seeing a number that's larger at 13. So if you're looking at it from this angle, you're going to say, oh, the length is 13 mm. Whereas if you're looking at it from this angle, you're going to see, oh, the length is 11 mm. So that's why we cannot place our eye at an angle like this. You must look at the scale straight on like this. So just a note, when it comes to your examinations, if you are asked to explain how to overcome a particular error or how to make a reading more accurate, you can say that you want to avoid parallax error, but you cannot just say to avoid parallax error, you must describe how. So you can use this as your answer in your exams. To avoid parallax error, the eye must be placed perpendicular to the scale. Let's look at another example of a parallax error. So when it comes to the measurements of volume, where we want to look at the volume of a liquid in a container, we must place the eye at the correct level of the meniscus. So what's a meniscus? The meniscus is the curved surface of the liquid. Sometimes you might get a liquid that curves upwards like in A, or you might get a liquid that curves downwards like in B. Whichever the case, the eye should always be placed level with the middle of the meniscus. So for example, in A, because it curves up, the middle is at the bottom of the meniscus, so you place your eye level in line with the bottom of the meniscus. Whereas for B, the top of the meniscus is the middle, so you place your eye level with the top of the meniscus in B. I suggest you do not memorize bottom or top, you're going to get confused. Just look at what's in the middle, make your eye level with the middle of the meniscus, whichever the case, whether it's A or B. Now, let's look at another error, which is the human reaction time. So, when it comes to starting and stopping a stopwatch, the human reaction time can cause the time recorded to be higher or lower than the actual time. I mean, think about it, right? Let's say if you want to oscillate the pendulum, by the time you let go, you press, and when it stops, you got to press again. So whether you are doing both at the same time, or if you're doing this with your friend and your friend says, okay, start now, there's always going to be some difference in terms of the reaction time. Some people may be trigger happy and they press too quickly, or some may be a little bit slower and they press a bit more slowly. Sometimes it's not just your pressing, sometimes you've got to press extra hard before the timer actually starts or stops. So that all just adds on to the total value of the time. So that's why we don't measure only one value for a very short time, like the period of oscillation. We take the time for many oscillations in order to average out the error. Because yes, there will be some difference in time, whether there's a time delay or a little bit too fast when it comes to pressing the timer. So by taking many oscillations, whatever difference in time that was caused by the human reaction time, that averages out the error, meaning it minimizes that value because it's spread out over many oscillations. That's what it means when we say to average out the error. Now, besides human reaction time, there are also other kinds of human mistakes. Sometimes mistakes can happen without us realizing it. For example, we might spill the water when we're measuring the volume and we didn't realize it. Then we're like, okay, that's a volume, and we record it. Look, it happens, right? So that's why we normally do repeats in order to be able to catch any errors like this, to catch any outlying data that could be caused by a mistake that we didn't spot. And there could also be mistakes that are not due to humans. For example, if there are changes in the environment. Some of these errors are caused by factors not within our control. For example, a change in temperature, or suddenly there's wind blowing, that may cause some of the experiment results to be different from what we expected. And now let's talk about improving the accuracy of our measurements. So there are some tools we can use to help us improve the way we take our measurements. So for example, you could use set squares. When taking measurements of length of round objects with a ruler, for example, if you want to measure the diameter of a coin or a tube, because they're round, it's not so easy to be able to find the exact point where to measure the diameter. So by using set squares, which are these triangular rulers, it can help us to improve the accuracy by aligning the edge of the circle correctly to scale. When using the set squares, how you do this is you place one of the straight edges on the meter rule and make sure that the other straight edge, the perpendicular straight edge, is touching one of the sides of the circle. So as you can see from this diagram is correctly using the set squares to measure the diameter of the circle. This enables us to make sure that we're taking the largest distance across a circle, which is the diameter of this circle. In addition, when measuring round objects, normally to improve the accuracy, we would have to take the diameters at different points of the object. So for example, we would measure the diameter at every quarter rotation. That means you've measured the diameter here, rotate this a quarter, then measure again, another quarter, measure again, another quarter, so you get about 4 measurements around the circular object. Or we could take it at different parts along the cylinder. That means like if you have a tube like this, you won't only measure the diameter on one point of the tube, you'd measure it on several points along the tube. Why? This is because the object may not be a perfect circle, so you'd calculate an average, or you might find that the tube also not a perfect cylinder and you need to get the average of the entire tube. That's why we take the measurements several times at different points. And that is it for this lesson. So if you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. Of course, if you just like to have more free lessons, that's fine. Just subscribe for more free physics lessons by your physics teacher, Ms. Ho. Do check out my website, physicsrocks.com, for notes, quizzes, and syllabus updates. Happy studying!